use Scantrons for your tests?
No.
Okay.
Are you serious? You don't know what's happening.
Well, I kind of beginning with
I just was wondering if you got my email.
I did. I think I just responded to you.
Oh, okay.
That it would work.
Okay, perfect. Do I get some sort of notification about it, or?
No,
Or
I'll
just
just
show up?
email you when I physically have the exam over there.
Okay.
And from what I understand, they don't do appointments anymore in the testing center.
Okay.
You just want to double check. Actually, I'm not sure they're open on Friday. I think they are. Oh my gosh. Oh no, they're open Friday, my bad. They just open at
8:30. That works. Perfect. Okay.
Yeah, but I don't think you need an appointment, so I think you just show up now.
Okay, cool. Thank you.
Morning.
girl this weekend.
That's good.
I have a question about this one. So I was checking my work on these, and then if this is the initial, like this N1 here, this is the initial, correct?
Yeah.
So in your online, I was checking my work. So it went from this to this. Now it makes sense when I say it out loud.
Well, it could be, because I don't know what you got when you did it, but the only weird thing that happens when you go like from 2 to 5 versus 5 to 2,
Okay.
because the energy and the wavelength is the same, it's just you might technically get like a negative number.
Okay, yes, so,
But then-
okay. Here is where it finally sits, right? So 5 would be here. But in your online, this is the way the problem's set up. That's the only reason I wanted to ask you. I was like, wait a minute.
Yeah, and
So this is the final state it goes to, right?
yeah, and so I think the answer key was just set up that way because to give you a positive number, unless it gives you a negative number.
I don't know, I haven't worked it out yet. But I just wanted to confirm. I was like, wait a minute.
But it ultimately doesn't matter because it's just, you want the difference and then that gives you a value and then you want the wavelength to be positive.
I also want to get it right. Okay,
Well,
I'll
you just
work
want
it
to
out.
get the positive number because energy can be formally positive or negative depending whether you're putting energy in or out of the system,
Okay.
which is kind of confusing. So that's why it's just like, just take the absolute value of the energy.
Okay.
And then same thing for wavelength. Like, obviously we can't have a negative wavelength.
No. Okay. I'll do it both ways.
Yeah, it should be the same.
Okay.
So based on this, I'm just having a hard time.
So the problem with this chart is, so the wavelength is in nanometers.
Okay,
So,
and that might be why I'm having a hard time. I'm just having a hard time understanding why this wavelength is in the visible region.
yeah, so then that's 5 times 10 to the negative 7 meters. Multiply it times 10 to the 9th. So that gives you 5 times 10 to the 2nd, which would be... Yeah, I don't like that chart. Maybe I should print out a better one because people keep complaining.
Honestly, it's just moving from 10 to the 7 to 10 to the 9th nanometers. I was like,
Yeah. Well, I don't know why the book gives it to you in nanometers, but
you have a different one in the notes, but it's kind of hard to, for me, it's kind of hard because it goes into the point, so it's kind of hard to see where the bands are. So this one was easier to read, but obviously not. So.
Right, let's get started. So I'll make a few announcements. So first of all, did everyone see my tutoring email about how to find Kevin Colhane? So hopefully you can bother him, give him some work to do, and keep him entertained. And so if you have trouble finding Kevin still from those directions, just let me know and I can give you his email and so you can connect with him over Zoom. And so other announcements, so Clubs Days is tomorrow. And it's also Fiesta Latino, or Latina. And let's see, let me pull it. So I think both of those are going from 11 to 2 tomorrow on this campus. And I think there's going to be a salsa competition. So I'll be making salsa, so you can come eat salsa. I think there'll be other food. And I'll also be pimping out Earth Club. So if you want to join Earth Club, I'm the faculty advisor for Earth Club. We did an event last weekend. We went out to Ashland to the U.S. Field and Wildlife lab. So they have a forensic lab out there. And we just helped rehabilitate their pollinator gardens. So that was fun. And we do hikes and stuff. So you can come see what other clubs are happening tomorrow. And so I'll put Wednesday. And then other things while I'm thinking about it. So if you're like food insecure or need help, don't forget RCC has tons of resources for you. So there's Aussie's Covered. I don't think it's on this campus, but you can order food, I think. And then I don't know if they have it pick up here. But there's other benefits. There's also care funds, gift cards. So there's resources out there for you if you need help. And so other announcements, so don't forget next week is our midterm. So we'll do a review on Tuesday and do the actual midterm on Thursday. Yes. I will do a review. I will post a study guide, but the study guide just like lists all the topics. I don't know if it's that useful, but I will post that. And And then email me if you need a makeup exam, or labs, I mean. So if you need to do labs 1 through 4, I have that tentatively on the 21st, so that would be a Friday. Maybe like a Friday afternoon. So email me if you need a makeup labs, and hopefully this works. If this doesn't work for your schedule, let me know. So far no one said that it doesn't work. So this is, again, just kind of my tentative date for that. Any other questions, comments before we hit lecture? And then if you need to make up quizzes, just email me. And we can either do them in lab or in the testing center. So most of you have been doing that and keeping up with that. All right, so let's shift over to lecture. And so now we're going to be looking at the Heisenberg uncertainty principle. So now we're kind of building upon what we were stating last chapter. And so this is just a recap. So we're back to this double slit experiment. And so we said, right, they did light first. They found that light gave that weird diffraction pattern, right, the interference pattern of bright spots, dark spots, bright spots, dark spots. That was kind of weird. And then so we said that they repeated this experiment in the 1920s with electrons. And so again, they're trying to determine what are electrons, are they particles, are they waves? And so they said, well, if the electrons are going to behave like particles, they should just pass through the slit and hit the spot, just like a ball would, right? You can imagine what a ball would do. It would go through the slit and then hit our screen here, our detector. And so, of course, what they actually found is that the electrons also made that same interference pattern that the light does. And so now, this is proof that electrons have a wave nature. So electrons are presenting this interference pattern, demonstrating they behave like waves. And so the other kind of problem is they were trying to study these electrons, and so the moment that you start trying to study them and you do something to study them, you've essentially disturbed the system. So, for example, one thing that they tried to do is, so if an electron's going to the source, they tried to determine, well, which slit is it going to go through? But the problem is the moment that you start trying to capture which slit it's going through, then it suddenly behaves like a particle, just picks one of the slits, and then hits the back like a ball would. So as soon as you start messing with it, you start perturbing the behavior. So even a beam of light. So you have these beams of electrons going, they're making the interference pattern, and so you shine a light on them, and that already disturbs them. So very difficult to study them. And so we're trying to figure out an electron's properties. And so we can say the electron's characteristics can be described as follows. So we want to try to describe its position. So that's what you normally do with matter. But again, every time you try to measure the position, where is it? Now you're disturbing it. You're stopping its track and you're messing up its position. From an energy perspective, so we want to know the wavelength, the frequency, and of course we know it's a wave. It gives us this interference pattern. And so again, the problem is we can't observe both properties simultaneously. So as soon as you try to observe one, now you're perturbing the other. And so this is kind of the conundrum here. So the wave and particle nature of the electron are complementary. So again, as soon as you try to observe one, like they did, which slit is it going through? Now we've messed up the wave nature. Now it's no longer acting like a wave. So the more we know about one, so we know the position, now we've destroyed the wave. So the less we know about the other. And so then Heisenberg kind of came up with this uncertainty principle then as they're trying to study it, and he kind of noticed something, because again, right, you shine a light or something to try to get its position, try to measure something, and you've perturbed it. And so he stated that the product of the uncertainties in both the position and the speed were inversely proportional to the mass. And you sometimes see this written as momentum. So mass times velocity is also momentum. But I've given it to you in this form, where basically your uncertainty in your position times your mass times your uncertainty in velocity is going to be greater than, and this is Planck's constant divided by 4 pi. And so you might, again, see it in this form. So delta x, delta p is at least greater than Planck's constant over 4 pi. So again, momentum, and momentum equals mass times velocity. And so, of course, this differs from classical physics. So in classical physics, we know that particles move in a path determined by its velocity and position and forces. And if you're in physics, you've probably done a bunch of equations and tested this. So you can, right, measure how the arc of a ball, calculate the angle that it's going. You'll know where it's going to land, right? So this is very basic physics. So you can calculate trajectories. But with quantum mechanics, we can't know that. So we cannot know both the position and the velocity And so we can't predict the path. We can only make a probability density map. And so if we're kind of comparing, right, a classical versus quantum mechanic trajectory. So our classical trajectory we can predict, we know it, we have equations to define this in classical mechanics, versus a quantum mechanic map, we can only say, well, you know, the electron's somewhere here. It has the greatest probability. You can see where it has the darkest shading. So this is the greatest probability that it's going to be here, but it could be here too on these outer edges. We don't know. Somewhere in there. That's all we can say. And so now this leads us to Schrodinger's equation. So Schrodinger's equation, we can only solve for a hydrogen atom. And so it only has one electron, and so we can solve it. And so we're not going to go deep into this. We're just kind of appreciating what was observed. So this is a Hamiltonian operator. So this just gives like all the possible states that your electron could be in. And then this is our wave function. And this is equal to energy operator times your wave function. But again, all we need to appreciate, so we can only solve for the hydrogen atom. So now what do we do with the rest of them? And so we can use computational chemistry and kind of get an approximation, but then we'll also find that we can use this MO theory, and it represents these different orbitals, and we can use MO theory to, again, give us a greater understanding of what's going on. And so what's going to be important is we're going to look at these plots of the wave function, and so that just gives us the pretty picture of the orbital. So all we need to understand is what these orbitals look like. And so the probability density function, again, just represents the probability of finding an electron at a particular point in space. And so there's a couple of different ways to represent that. So this is just your 3D representation, so XYZ axis here. And we have our smatterings, again, showing where our electron might be. And so this is a 1s orbital, and it takes a sphere shape. You have your radius there. And so, of course, you can tell, right, high density in the center, so higher probability of finding an electron. And then as you go out towards the edges, less shading. So still might find it hanging out there, but less of a probability. And now this shows the same thing, just as a function of radius. So again, you can see highest probability is when you're extremely close to the center of your atom, and then it decreases, of course, as you reach your end of your atom there. And so again, this is just another way to plot it, the radial distribution function. So this is just distance from your radius, probability. And so the maximum probability is going to be at 52.9 picometers for this particular instance. So this looks to be the 1s orbital of hydrogen. So at that distance, that's the most likely place that you're going to find the electron. But of course, it either decreases before or after that. And again, it's all just a probability map. So now let's look at these quantum numbers. And so we have these quantum numbers. We'll go through them. And so these are solutions from our wave function. And so we have calculations. Again, this is where computational chemistry originated back in like the 1920s. Is, okay, well, we can't solve even the helium atom, so now you add 2 electrons, and you can't fully solve it. But you can use computers to at least get a closer and closer and closer approximation to what the answer is. And again, this gives us these pretty pictures that we're going to be looking at. And so the first one is called your principal quantum number, n. And so this just corresponds with your periods on the periodic table. So, right, you start with 1, and so that starts with the s orbital. And so I'm just going to start another note. So principal quantum number, so 1. And so values of n can be any whole size integer, so it'll be 1, 2, 3, and 4 essentially that we'll be looking at. So you can go on and on theoretically, but for, again, practical purposes, we'll stop at 4. And so looking at the next number, so the next number is called the angular momentum quantum number. But all this is telling you is, well, what shape is the orbital? And so now if we go back to our s orbital, and so your L has allowed states. So your L has to equal to at least n minus 1. So these are the only allowed states. And so all this means is for our first quantum number, energy level 1, we only have an s orbital. So that's the only thing that's in there. So 1s. And then so for the rest of the quantum numbers, so you have your next one is the magnetic quantum number. And so this just tells you your specific position. And it can take values of either L, so it'd be 0 to integers plus L, or integers to negative L. So if we go back, so first level, we only have the 1s, but then there's only one possible position, right, for our s orbital. This is L equals 0. And then mathematically, we don't have any other options. So back to the formula. My magnetic quantum number has to equal to no greater than L. Well, L is 0. So my m sub L can only be 0. Again, this makes sense, though. There's only one s orbital. So we wouldn't need to indicate anything else. So 1s. And then the last number here is ms. So this is just the spin of the electron. And you only have 2 possible answers. So it's either formally spin up or spin down. And the only thing is, so 2 electrons cannot occupy the same position. So if you have 1 electron and spin up, and let's say you were doing helium next, the other one would have to be spin down. And so the other way to think about these quantum numbers is they're kind of giving you a coordinate system of where this electron is located. So now for this first one, we have n equals 1, L equals 0, m sub L equals 0. And so let's just say I have 1 electron, so this is hydrogen, and I put it up, and so I just put spin 1/2. You could, again, so 1 electron, you could say, well, maybe it's actually in the down spin, and it doesn't matter, we don't know, we can't really say. All we know is this could be another position. So both of these are allowed, and they both indicate that you have one electron in the 1s. Everyone following for now? And again, just correlate it to your electron configuration. So all we're doing, right, we looked at hydrogen, 1s1. We wrote out our quantum numbers for that electron, or at least our possible sets. So we have two possible sets. So I'll write 1s1, 1s1 for our electron configuration. So these are, again, just two possible states for this one electron. So if we do helium now, for instance, in 1s2, that means that one electron, so E number 1, let's just say it would have to have an n equals 1, L equals 0. And if we put this in a spin plus 1/2, then our second electron, again, it can't be in the same position, right? Because that's part of our rules is no electron can occupy the same position. So it would have to be n equals 1, L equals 0, m sub L equals 0, and m sub S negative 1/2. And so this is, again, just showing this representation, giving you the quantum numbers for that. So now back to our electron configuration periodic table here. So we started with our first level. Now we're going to 2. Oh, before we go to 2, so just looking at s orbitals. So s orbitals, they're all spherical. And so, of course, they're the lowest energy orbital in any principal energy state. So all that means is your s orbital is the lowest. We're looking at that, right, when we fill up our electrons. And then there's also this number of nodes. And so a node is just an area of no electron density. So your first level would not have a node, so you just have the 1s. But then if you go on to the 2s and 3s, and we might have mentioned this before with the little pictures, but there's the 1s here, then there's a node, so an area of no electron density. Then the 2s starts with the spherical shell around the 1s. And then if we look at the 3s, so 1s, 2s, now there's a node there. Then you start the 3s. So that's all it means by nodes. So again, you can just use that formula, or you can kind of see it's always just one less. All right, so now let's look at our next level. We'll start, so principal, quantum level 2. And so we still have our s orbital allowed there. You know, again, we see that from our electron configuration. So we start the s's there. Now we have 2s. And what other orbitals are allowed, though, now in the second level? Do you remember? I heard someone whisper it. P's. So now we start our p block. So we said that that started over here. So 2p. And so again, let's look at our quantum numbers. And so I would write this somewhere. So your s orbitals, again, they have an L value of 0. But now we have the option. So we just said L is equal to n minus 1. And so now we have the possibility of having a p orbital now. So p orbitals are indicated by L equals 1. And then, so we know that there are 3 p orbitals. So pz, so that's just formally up and down. So pz is usually defined as the principal rotation axis. And then px and y just kind of depend on your orientation. So I'm doing px going across, and then py is going in and out of the plane of the board. So we know that there's 3 of them. But now this also matches with our m sub l. So remember, m sub l, they're just specifying like which one of those p orbitals now. So we said, so p orbital is equal to L equals 1. So that's our p orbital. And now, again, our m sub L values are going to be equal to, in this case, so negative L to 0 to positive L, which gives us negative 1, 0, and positive 1 for our 3 possible values. And then, you know, it doesn't really matter who's who. You could just kind of, in your mind, assign, all right, well, one of those means one of those. Again, you can swap these axes around. But it's just, again, a coordinate system. It's kind of telling you where is the electron located. So let's say we wanted to look at boron. Let's look at boron now. And you might have a question, you know, what is a valid set of quantum numbers for a valence electron of boron? And so let's look at the possible different answers that we can give. So let's just start with what's our electron configuration for boron. Or 2p, right? 2p, 1. So we have 1s2, 2s2, 2p, 1. And so our valence electrons, so it has 3 valence electrons, so it could be any one of these. So let's write out our possible quantum numbers. So somebody give me a set.
I have a question. So why is it the 2s2 also included in the valence electrons when it has a pair, right?
Yeah, well, this is kind of tricky. So usually you just look at the outermost shells, and then we are making a distinction between the S and the P. So we've kind of mentioned this with our trends, like as we go from beryllium to boron with ionization energy, how boron actually has a lower ionization energy because it only has 1 filled in the P.
Okay.
But it's still considered valence just because it's not the core, so as long as it's the outermost.
Okay.
So what's one possible set of quantum numbers? So we have N, L, M sub L, and MS. So what's going to be my n, first of all, if we're looking at valence electrons? 2. Let's put a 2 there at least. And so then there's 2 possible quantum numbers for L now. So what are my possibilities? So we could do 0 or we could do 1. Let's kind of do both. So if we do 0, that means that we're looking at our valence electron in the 2s orbital. And so if our L is 0, what's my only option now for M sub L? So 0 exactly. And then MS? What did you say? Plus? So plus 1/2, and then you could also put, negative 1/2 if you're feeling it. It doesn't matter, either one. So that's one set of valid quantum numbers. So what else could we write? So let's look at our next one. So we said that we could also indicate a 1 for our L. So what does the 1 mean again? What kind of orbital? Our p orbital. So now this is showing, okay, this is some electron in our 2p. And then, so what should we put for M sub L? So we could do either -1, 0, or +1. So again, that's 3 separate scenarios. Is that clear, or should I write them all out explicitly? Yeah. Let's, because we could have a combination. So -1, 2, 1, 0. 2, 1, +1. And so all these are valid. And then what about our M sub S? So what are our only options there? So we could do negative, what'd you say? So either -1/2 or +1/2. Doesn't matter. So for our P, we should have, 6 possible quantum numbers then with all the different combinations of where your electron could be. So does that make sense for this one? So all these would be, again, valid answers if you're asking for the valence electron. You just want to make sure that no rules are being violated. So, I couldn't do 2, 0, 1 again, so that's not possible. That doesn't exist. So that's how I would trick you on an exam, like a multiple choice question. I would put some not allowed quantum numbers. And so let's look at our pretty pictures now of the p orbitals. So again, this is what they look like. And so the p orbitals already start with a node. So they have a node right between them. And their shading, when we draw MO diagrams, are opposite. And this is more like a mathematical formality. Now let's go to our next row. Let's go back to our electron configuration for a second, kind of review and orient. So we said 2p, then we started our principal quantum level 3. So we know that 3s is allowed, 3p, we'll skip 4 for now, but then we know that 3d is also allowed in there. So this is our new orbital that's allowed. So let's do principal. Quantum level 3. And so now what's allowed in there is the 3s, of course, L equals 0, our 3p, L equals 1, and now our 3d, or L equals 2. So let's take a look at our d orbitals. So we have 5 d orbitals, and so now this m sub L makes sense. So if L is 2, these are the 5 m sub L values, which correspond to the 5 d orbitals. So -2, -1, 0, +1, and +2. And so again, it doesn't matter who you formally assign to who. And so here are the pretty shapes. And so d orbitals, this doesn't show the shading properly. So they would look like this. Again, this is mathematical purposes why I shade it this way. And so a lot of them look like this with a shading, just in different orientations. So this is called DYZ. So notice it exists in the YZ plane, so Z is up and down. Y is going across from them, so it's in that plane. DXY, so you can see this is in the XY plane. And again, it would have that same shading. Oops. It would help if I could draw. So again, shaded like this. DXZ. So same thing, so now it's in the XZ plane, so going up and down and then in and out of the plane of the board. Again, it would follow this shading pattern. Dx squared minus y squared, its difference between xy is that x squared minus y squared lies on the axis. So if I were to draw it, so x, y, on there. And then the what I call the funky one, so it's the only one that doesn't have this kind of 4-leaf clover pattern, is this dz squared. So it's in your principal rotation axis, and the proper shading for that is something unshaded and then a donut hole shaded around it, or vice versa. Now let's go back to these, practice writing. So let's just look at, let's just say iron, why not? So we have iron here, so 4s2, 3d6. And so let's just say, what is a possible set of quantum numbers for a valence d electron in iron? And so again, I'll just grab the electron configuration. So starting at argon, so 4s2, 3d6. And so what are some possible values then for quantum numbers? N, L, M sub L, M S. So what would we put for N? So what's our principal quantum number? Because remember, we have to have a d orbitals allowed. Because if we did 2, that'd be L equals N minus 1, so 2 only allows S and P. Yeah, so 3. So 3. Now that gives us all the possibilities of 0, 1, and 2. So S, P, and D. And then, so what do we put for L? So 2, so indicating our d orbital, since we want to again indicate our position. And M sub L? So I will do the same thing and write them out. So excellent, I heard all the values. And you don't have to write them all out. I'm just showing you all the possible numbers. So all of these would be valid. And then what about our MS values? What could we put there? So plus halves and negative 1/2. So any of these would be valid. So you should have 10 possible, or 10 different quantum number sets, so that would correspond to a total of 10 total d orbitals, and of course you can just pick one valid one. Yeah?
So like on a test or something, if we didn't write it all out like that, how would you want us to write the MS?
Oh, just, like you could just pick one. So if it was a free response, like on an exam, you know, you could just literally pick any one of these values. So 3, 2, -1, -1/2. But the other, like I was saying, the other scenario would be like a multiple choice question. And I would give you like 3, 3, -2, and be like, ah, that's the wrong one, you know, that sort of thing. Other questions? Definitely ask questions. There's a lot of things going on, so. And so now let's continue to our last principal level. So let's go back to our periodic table for a second. So 3D, and so 4P, 5S, 4D, 5P, 6S, and so this starts, 5D, I got overexcited, and then 4F down at the bottom. So now once we have our quantum number of principal quantum level of 4, now we can have our F orbitals. So principal and so now for our principal quantum level 4, so we can still have our 4S, we still have our 4P, still have 4D, and now we just get 4F. And so I'll just rewrite, so L equals 0, L equals 1, L equals 2, and now L equals 3 for our F orbitals. And so let's look at the pretty pictures of F orbitals. So I have never drawn F orbitals. I guess part of that is I never did F orbitals or F block in any of my research, but I would not expect you to ever draw this out. I don't generally see that. But just appreciate the pretty pictures, appreciate that there are 7 of them. So highlight if you need that. Okay, there are 7 f orbitals. And again, those correspond to our possible m sub l values. So we said if L is 3, m sub L is negative L to positive L in integers. So that gives us 7 possible values of negative 3, negative 2, negative 1, 0, 1, 2, and 3. So 1, 2, 3, 4, 5, 6, 7 matches up again. And so let's do a practice. Let's just pick free sodium here. So 4F. And we could argue about the different electron configurations because this is a weird one. So we could have had like 5D1, 4F2 or something. But so let's do an example. So write the potential quantum numbers for the valence electron in the f orbital for pre-sodium. And again, experimentally, you would have to determine the 6s2 4f3 for the electron configuration. Who was before it? Xenon. So xenon 6s2 4f3 or 6s2 5d1 4f2. But again, we'll just focus on a potential coordinate for the f block. So now let's write out our potential scenarios. Oops. So we have N, L, M sub L, and MS again. So what do I have to put for my N? So 4, so it has to be 4 since we're starting our F block. And then L, what's our L? So 3, again for our F block now. And so what are all our values of M sub L possible? Excellent. Negative 3, negative 2, negative 1, 0, 1, 2, 3. So now we're going to have 14 values. And so what are all my possible values of MS? So plus and negative 1/2. Excellent. And so again, you can pick any of these combinations. So 4, 3, 0, negative 1/2. 4, 3, negative 3, positive 1/2, etc. You just can't have any violating numbers. All right. Yeah.
Can you go over where you got the M sub L values?
So the M sub L, so just mathematically, that's just a formula. M sub L is equal to negative L with integer values to positive L. And so because we're looking at the F orbital, right, we have 3 for our L. So then these were all the possible M sub L values. And so there should be 7 because they correspond to the 7 different F orbitals. So we're not defining who's with whom, but we just need to know that there are 7 of them. So again, it's like a coordinate system matching up to whatever F orbital. So does that clarify. And then, so this is just another summary chart that's from your book that I kind of like. And it just rehashes all the information we went over. But then it also emphasizes, again, that kind of elementary school electron configuration that you might have learned, where you had like n equals 1, and there were 2 electrons in there. And then the n equals 2, that it had a total of 8 electrons. So that's where all those numbers are coming from. So we see, right, our first principal level, it only contained an s orbital. So it only has 2 electrons in that first shell. So that kind of matches with your elementary school or whenever you did this junior high atomic structure. And then now with our second principal quantum level, right, we said now we have an S and a P are allowed. And so those P shells hold 6 electrons, and we know, of course, the 2s holds 2. So that gives us our 8 total. And again, all our possible quantum numbers, so it's showing you explicitly, it's now our P. Again, 3 possible m sub L values for our 3 P orbitals. And then going down, so now third shell, so third principal quantum number. Now we have S, P, and D allowed. So now we get 18 from 10 in the D, 6 in the P, 2 in the S. And again, all your possible quantum number values for m sub L for D. And of course, all your ms values. And then the fourth shell, we say it holds 32 electrons, since now we have 14 from the F, so 14 plus 10, 24 plus 8, so that gives us 32. And again, all your possible quantum number values. So any questions about this? Again, whatever you need to do, so know that your L's just tell you what shape it is. So again, L is 0 is S, L is 1 is always a P orbital, L is 2 is always a D, L is 3 is always an F. Let's see, so let's try another type of question. So sometimes you may have to do kind of the reverse. So what, oh, why is that so light? What element corresponds to the following set of quantum numbers for the valence electron? And so your numbers, so N, L, M sub L, M sub S, so 6, 0, 0, plus 1/2. So what element might that correspond to? So take a minute or two to think about it. I was thinking yes.
Isn't it open note?
Yeah, because it's open. No.
Just 'cause I don't want to learn P tables. Use it,
So did we find an answer? So what element might it correspond to? So I like cesium. You could have also given me barium potentially, but either one of these two is, so let's go over. So principal quantum level was 6, so then we had to start on the 6th level. Then the L corresponded to the S, so that had to be something here. And of course we weren't given any other information, so either cesium or barium would be valid answers. Do we want to do another practice like this?
Yes.
So Marissa, would, for example, potassium and calcium have the same?
Yeah, they would have like the same quantum levels. Yeah, unless you were given more information, like, you know, it has 2 valence electrons or something. It's just you weren't given that much. So let's try another one. So which corresponds to, so 3, 1, and so again, there could be multiple answers like you saw with the first one. Do we have potential guesses? What did you say? So chlorine would be valid. So aluminum, so any of these would work. So we don't have too much information. They didn't tell us how many valence electrons. All we know, it's something in our principal level 3. We know it has a p orbital. And then, you know, again, we don't define which one's which, so we don't know where it's really at. So any of these would be valid answers. So aluminum, silicon, phosphorus. Since it didn't specify anything and it was just asking about the valence electron, could be any of those. Any questions about this? Again, ask questions. It's kind of a lot, and I think it always looks scary with all these numbers and symbols.
Can you give us one from another one from the transition metals that is like kind of in that same format? Where you give us the quantum numbers?
So let's do. So which corresponds. Oops. I'll try to specify. So see if you can find what corresponds to this quantum number, and I gave you additional information assuming that there are 5D electrons, which still might get multiple answers potentially, but. So do we get an answer? So who might it be? So it could be the whole 5D row, and then I try to give a hint of which one has 5D electrons as well. So which one would that correspond to? I was thinking rhenium, but because it should be 5D1. So 5D1, 2, 3, 4, 5, ideally. But somewhere on this row, so at least if you got to here, you knew, so this was 5 for our principal quantum level. D gave us the 2. And so again, that meant any of these, and I try to give a hint of who has 5D electrons, so giving us rhenium. Other questions on this, or? So let's at least look at this page of notes. And so we're seeing and I think we've kind of already gone over this, but we'll kind of recap. And so like we saw with our periodic table, so why we're doing this in the order and going across and filling them in is that it corresponds to our atomic orbital's energy level, and this obeys what's called the Aufbau principle, and that's just you fill the lowest orbital first. So that's what we've been doing. We always start with the 1s, 2s, 2p, and this graph is just another representation of that. So again, you can see the order they go in, and again, note that the 1 to 2 has the greatest energy gap, and then the subsequent ones get smaller and smaller and smaller. And so again, that's why you get more and more weirdness and craziness as we get to the higher energy levels, since they're really close, so then they can kind of swap around, trade electrons, and do funky things. Again, giving us less predictable electron configurations. So that's all that that means. And so we kind of have gone over this just by nature and filling in our quantum numbers, but we're seeing that again, they exist in just orbitals, and they all have a unique quantum number, so they all have to be in a separate configuration. They cannot occupy the same spot. And so we did electron configuration, and then we're just translating that electron configuration to all these different pictures, essentially. So I like to use, the little line representation. Your book tends to make these little boxes, but they all mean the same thing. And so again, we saw the spin, and so spin, it's just the state that the electron is in, so it's quantized, so it's either spin up or spin down. And y'all did an excellent job of giving me, again, those two possibilities. So it's always +1/2 or -1/2, just in formalities. And so by Pauli exclusion principle, all it's saying is, again, your electrons can't occupy the same position, so you can't have two spin up. So that does not make sense. It violates what we just learned about quantum numbers, that they all have to have unique quantum numbers. And so we'll look at some things in detail later. So paired spins are called diamagnetic, and that is just like that. So this would be diamagnetic. If you had, let's say, some degenerate p orbitals that were doing something, and then you only had one electron in each one of these, this would be called unpaired, so they would be paramagnetic. And so kind of teasing, so later we'll prove why oxygen is paramagnetic. And so again, no two electrons may have the same set of 4 quantum numbers. So it's like a unique coordinate system, which we saw. And so again, filling up from the lowest to the highest, just showing you the other representations of this. So for example, here's their carbon, how they draw them with the boxes and the 1s, 1p. So we're used to this orientation. I'm not really sure why they picked the boxes either. To me, they don't really mean much, and they don't really help you going forward and making MO diagrams, but I guess it's just a convenient way to write it on one line, ultimately. And what we keep saying, so orbitals that are in the same sublevel have the same energy, aka they're degenerate. So, for example, that's why I write the p orbitals, again, all in one straight line. They're the same energy, unless, of course, we're doing bonding, then we'll see when they're not. And so Hund's rule is just you fill up the orbital before completing a pair. And so anytime you complete a pair, you have to pay an energy price to pair them. So it's more favorable to not pair them, of course, until you have to. And kind of seen this already, but again, just a recap so we're all on the same page. So we've looked at the electrons in our lower energy shells. So again, we always refer to them as the core electrons. We've seen the big gap in the ionization energy telling us when we're ejecting core electrons. And then anything else is considered our valence in our outermost shells. Again, usually just the S and the P's. And we kind of ignore the transition metals. Yes.
Okay. Oh, right, okay. Sorry, stupid question, I think.
Not stupid. Yeah. Just anytime you start like the new principal quantum number, that's a big hint. And then again, the D's get odd because you usually just focus on their D electrons and ignore everything else. And so, of course, the valence electrons contribute to everything, so that explains, why they behave this way. And again, as we're kind of building all these pieces, it may not feel like it, but you're getting to a more and more sophisticated understanding of chemistry and how things bond and how their orbitals interact from this. All right. Let's go ahead and probably stop here for today. Yeah, so that'll be a good stopping point. So again, ask questions. Make sure you feel comfortable with all this. It's kind of a lot, but hopefully it kind of feels like it's reinforcing itself at this point. So electron configurations should now be reinforced by quantum numbers. Just everything should kind of keep building. And then I will see half of you in lab today. So I believe it is flame test lab today.
Remember to tie your hair back.
Yeah. Tie your hair back.
So I actually will be here the 20th.
Oh.
So I won't. I'm leaving the 22nd.
Okay.
I thought it was during the next week that we're taking it, so I won't need to go down to or anything.
Sweet.
Okay.
I have a bunch of assignments to give you. Do you want me right now or lab?
Oh, whichever's more convenient for
It might be
you.
like 10, 15 minutes late to lab. I have to go to a work meeting real quick.
Okay.
But it ends at 1. I'll try to sneak out early.
Yeah.
And then I do have to reschedule that quiz Thursday. We had to pull one of our family dogs down, so I forgot to email you.
Do you want to take the quiz during lab then, or?
Sure. Yeah, if there's time.
Yeah, let's aim for that.
Okay.
And then, yeah, you can either hand me stuff now or later.
I'll bring it. I'll
Okay.
Thanks.
I mean, I could just do it once.
Tomorrow's Thursday and my appointment's at 11. Would I be able to go to the testing center earlier that morning to take the midterm?
Yeah, we can do that if that
Okay.
works. Or
Sweet.
yeah, worst case, we could also do it like Friday or something.
Right.
If that works.
Yeah. I would just rather get it done the same day 'cause I don't like pushing things off. Do you know what time? Do I have to like schedule an appointment for testing center? Or
No.
I can just.
But then my partner.
Yeah, just let me know so I make sure to get the paper over to them
Yeah.
physically.
Okay. I think I'll probably go at 9
Okay.
Thursday then.
Yeah, that should work.
Okay. Awesome. Thank you.
Hey, I don't know if I missed something, but how do we access the journal articles? I was gonna ask you that last week, but I was sick.
Yeah, the
I
journal
was checking the
articles.
Blackboard and going to like the RSCC library and couldn't figure out how to find them all at once behind paywalls and everything.
Yeah, you might have to be at school, but it should make you log in.
Oh, like at school? Okay.
If you're at school, it should just work. If you're at home,
Yeah, because I logged into the library database.
Oh, yeah.
because you go here,
Mhm.
guide,
You have to go to guides.
and then chemistry, Journal of Chemical Education, and then
Okay.
if you're at home, once you click on this, it might prompt you for like your student login. But if you're at school, it should just work,
Okay.
and then you can search by publication.
Is it fine if I turn this on Thursday then?
Yeah.
Okay, thank you.
Okay, I'm not sure if I should go to the tutoring thing. I'm not completely lost, but like, when it comes to like all the, like mostly for like electron configuration, it's kind of confusing, like trying to figure out where everything is. Like when we were doing the last one, it was like rhenium.
Yeah.
And I thought for sure it was gonna be like that one, because I was looking at the like N5, and then in the
Well,
second, like,
Yeah, because you might want to write on there, because remember this is 3D, 4D, 5D, so that's where things get
okay.
odd, because I had given you 5D.
Yeah.
So it's like, yeah, that is 5S, you're correct, but then it goes back to 4D. So that's,
Where does it go back at? I guess if I had everything labeled. I would be
yeah,
sure.
so I would probably label it like, so this is 3D, and then it goes back to 4P. And then this is 5S, since it has a 5 there, but then it's 4D, 5P, and then back to 6S. Then, remember, lanthanide starts 5D, and then cerium starts 4F.
Oh, okay. Is there like 1D, or is that just not like this?
It can't exist.
It can't, okay.
Yeah, by the
Yeah,
quantum
that's
number.
what I kind of thought. It was like,
Yeah.
I don't know. I'm probably just gonna go over like electron configuration at home, but yeah, it's like sort of confusing still. But I don't know if I should go to the tutoring thing for that. Like,
Yeah,
Is that
I
worth
mean,
it?
it might, that's up to you. I don't know Kevin Colhane might be worth it. I don't
Okay.
know about, I don't want to speak badly of the person there, but he's like a student, so he's not like a trained
Oh,
teacher. But what you could also do to just check yourself is you go to the P table and electrons and then just kind of practice.
oh, okay, yeah.
And again,
Yeah, I always forget that's a good website.
yeah, and if you're off by an electron, because like look at niobium, that's a weird one because for some reason it only has 1 in the 5s and then sticks 4
Yeah.
in the D, and it's like you wouldn't know that unless you had
Unless you looked
experimental.
at it, yeah.
And
Okay,
so
kinda
that
makes more sense.
it's like okay, well if you had gone 5s2, 43, that's still fine.
Okay. Yeah, I'll keep practicing.
Yeah, and again, right where it starts, like write your 3D, the 4D.
Yeah, I'm gonna actually put that.
Yeah, because I swear, like, even I have to do it, I'll also be like, oh, I forgot.
Question. So, the lanthanum and actinum, I know that they are part of the D. They have D orbitals. Do you consider them to be lanthanoids and actinoids, or no?
That's a good question.
'Cause,
I feel like they are, just because they're called that, but then they, like,
well, so
kind of
my
formal.
sister, she's going to school at OSU. She's working on her PhD in chemistry,
Mhm.
and she's in a lab group that actually works with those
Oh,
specific
nice.
elements, and so she doesn't consider them, but she knows that some teachers do.
So she doesn't put lanthanides and actinides in the F block?
No, she said like in Latin or something, lanthanum means like lanthanoids or something like that.
Oh.
So it's like similar but not quite.
How far along in your PhD is it?
She's pretty. I mean, she just got her bachelor's like not that long ago, so she's in her first year of getting her PhD, but she's been in this lab group for a while. She actually, I don't even know how to explain it because it's like way over my head, but so they're working on different types of carbon capture.
Oh, that's cool.
Mhm. But she actually has so far created like 3 different, I don't know if they're compounds or what, but 3 different something that hasn't actually been in literature before. I don't know what it is, but
Yeah, I mean, that's what you do, is like you make new compounds.
Yeah.
I was actually gonna ask you if she wanted to give a talk or something to the class, just because that'd be cool.
It might have to be like over Zoom or something because she lives in Corvallis.
Yeah, that's what I was thinking, because we did that last year and had like a talk over Zoom.
I could ask her if she wants to. She's working on her PhD in like specifically teaching chemistry. So she teaches this class at OSU.
Nice. Yeah. I don't know, it seems like there's a big debate about it,
Yeah.
honestly. Because in 2021, they're putting it as the first of the F block elements, but
But
it's
it's
like
not
it
an
doesn't
F
matter. Yeah.
Yeah, I know.
So, I mean, yeah, I guess we could argue about semantics for a while.
Yeah, I guess it doesn't matter too much.
No, it is one of those funny, interesting things. And I don't know why they're just called the lanthanide and actinides, even though they don't have F blocks. But
Yeah. Well, and because the F orbitals have a total of 14.
yeah,
And
so
there's 15 in this row if you include the one.
exactly. So it's kind of weird, but
Yeah. Okay. I'll ask her if she wants.
yeah, if she just started, she may not want to, but I think it'd be cool.
Yeah.
She could,
'Cause I
yeah,
have no idea what she's like actually doing. It's like way above my head.
yeah. Yeah, I mean, that's the weird thing about PhDs, is like it's so specific.
Yeah.
Question?
Sorry, this laughed from a while ago, but I stress myself out over the simplest things, and I can't not turn this in because of it. So I don't know how to get it. My average error.
So I've forgotten what they wanted for this. Oh, okay. So for the percent error of average, so it's saying, so let's just assume that we want it to be 5 grams. That's like the true value. So then you just take,
For 5.
yeah, so the 5.08 minus 5 divided by 5. And it should give you a pretty small percentage.
Oh, okay. And then also. Sorry, these levers are so old.
Oh, don't worry. That's why I'd rather you like take your time and get them done correctly than just
this
rush.
one. I know it's simple, but I just can't.
Oh, 7?
That's it.
Oh, no, like what to do? Sorry.
Yeah,
So
7
it's
and
saying,
8.
so you kind of have to read through it. So, okay, we have a 15-gram object. It's placed in a graduated cylinder containing 25 milliliters of water. Okay, so it starts with 25 mils. You put in the object, and then the water rises to the 34 mil mark. And then, so what's the density? So we need to find volume of the object by subtracting first, so 34.0 minus 25. So that gives us our volume, and then we can just do density equals mass, so 15 divided by whatever the subtraction is.
Okay, I think that's where I was confusing myself. What's the volume? Okay.
And then, did you have questions on 8, or do you want to write that down first?
Yeah. Okay.
And then, so now this one, so we have a mass of 45.5. We fill it to 10 mils with an unknown liquid. So now it's kind of like the opposite. So now, right, we have to subtract to find the mass. So we have, so it basically, right, you took an empty graduated cylinder, you got the mass of it, filled it with liquid, new mass on the balance, 59.4. So you want to take that 59.4 minus that, so that gives you the mass then of whatever that 10 mil liquid is.
Oh, that.
And then you can find the density of just mass divided by volume. So whatever, 59.4 minus 45 divided by 10.
See, I knew it was easy. I was just. I do that.
Yeah, it's like sometimes you really have to like picture yourself in lab, like, okay, I'm going through the steps, I'm measuring.
I know. Like, I look at the simplest stuff and I'm like, I'm lost. But yeah, okay. Thank you.
Yeah, no problem. And then if you want to turn them in now, oh, you gotta finish, my bad. Yeah, turn them in whenever.
Okay.
Do you have lab today?
Thursday.
Yeah, so you can give them to me Thursday if you want.